Yeah, we're streaming. We're live.
Sounds good. I just sent you the slides. Well, uh, one thing before I start today's talk. Last time I listened, there was an echo. Is that on the YouTube?
There was an echo on the YouTube.
Right.
That
So
shouldn't happen. Uh,
so maybe you want to take a look
I'll
at
double.
it.
Yeah,
Yeah,
I'll double check if there's anything happening. But it should be probably it's a connection thing or something.
could be.
All the other videos are clean. I don't think it will be
Yeah,
a
yeah.
recurring
The
issue.
the other ones are all fine. Just last week.
Was it for the
Yeah.
entire video, the echo?
I don't know. I listened to the first couple of minutes.
Ah,
I
okay.
I
Okay.
don't
I'll
I
I'll
don't
double
like to
check.
listen to my own voice. I
I'll
bore
double
myself.
check. I'll see what's happening.
All right. Okay, so let's start with Chemistry Series 18. We're continuing with our thermodynamics conversation. The last two times, subparts A and B of thermodynamics, we kind of introduced thermodynamic concepts and terminology, nomenclature. And so starting from today, we're kind of going to go into a little bit of how thermodynamics affects reaction mechanisms and product formation, how some reactions are under kinetic control, some are under thermodynamic control. What can a chemist do to shift a reaction from kinetic to thermodynamic or vice versa, and all that. Starting from next week, I think next week its entirety it's going to be somewhat mathematical. We're going to solve equations for rate constants and equilibrium constants and the Arrhenius equation, things like that. So so far we're going to be conceptual, and so next week will be a little bit mathematical. So when we go to slide 2, we've seen this before. This I've introduced this the last two times. A are the reactants. B the products and their reaction. This is a graph of energy with respect to intermolecular distance, or actually internuclear distance. That is, the nuclei that are bound together through a bond in A separate out uh, in and form B. So the distance between the two nuclei is the x-axis, and the free energy of the molecules is on the y-axis. So we'll see A is where the free energy of the reactants are, B is where the free energy of the products are, and C is the highest point in that energy graph. We call that the transition state. So from transition state, either side will be energetically favorable to go to. So this kind of a free energy diagram, we're going to see it over and over and over again as long as we're talking about thermodynamics. So that was the general one. Let's go to slide 3, and in slide 3 we'll see uh, that I have shown what happens if a reaction is under thermodynamic control. What happens when reaction is under thermodynamic control is that the free energy of the transition state, that is delta G double dagger, is easily achievable. So the products can very easily undergo a reaction and form the reactants can undergo reaction from the products, and the reverse can also happen. That is, the products can react together and reform the reactants. That is, the reaction can go in either direction when we're looking at thermodynamics, except for some special cases that we're going to talk about. So four things are going to we'll see here that comes out of this graph. Number one is that if the delta G is negative, that is the situation in the forward reaction I have written. The G of reactants, G of A, is greater than G of products. So the free energy of the reactants is greater than the free energy of the products. So the sum of those is going to be a negative number. So delta G is negative. That is going to be a spontaneous reaction. That is, if in this reaction the activation energy is achievable, then the reaction will take place. We see this on a daily basis. Iron rusting, you don't do anything to it, right? It just sits there, iron and water, and it rusts. Why? It spontaneously rusts. Why? Because the delta G of iron oxide is much lower than, the G of iron oxide is much lower than the G of iron and water, and so we'll see that you have a delta G negative, the rusting of iron spontaneously takes place. Now, if delta G is greater than 0, that is, let's say, the reverse of this reaction, that's a non-spontaneous reaction. If the free energy of the products is much greater than the free energy of the reactants, then that reaction by itself doesn't take place. It requires an input of energy. So, for example, the reverse of iron rusting, that is iron oxide turning into iron and water, doesn't by itself take place because the G of iron and water is greater. But when we smelt iron ore, which is mainly iron oxide, we input a lot of energy into the system, and at the end of that, we'll get iron and water out. So basically, in a smelting, in a what do you call it, in a foundry, this is what you're doing, is that you're inputting a lot of energy to drive the reverse reaction. So it's non-spontaneous under the kind of standard temperature and pressure. Now, if the G of if the free energy of the product is much greater than the of the free energy of the reactants, that reaction goes to completion. You're not going to get any of the reverse reaction. This is exactly the same example of iron rusting that I was telling you. The forward reaction, that is iron reacting with water and oxygen to form iron oxide, is such an energetically favorable reaction that it goes completely to completion. That is, if you leave a piece of iron out there in the elements and you come back 100 years from now, 1,000 years from now, it is completely turned into rust. There's no more iron metal left. But if the difference between the G's, the free energies, is not that great, and the activation energy, the transition state, is accessible from both sides, then we will end up with a situation where it's just as easy for A to go through C to go to B than it is for B to go through C to get to A. That is, both the forward reaction and the reverse reaction under the temperature and pressure conditions that we're looking at, both of those are energetically accessible to us. in that situation, we're going to end up with an equilibrium situation, which means that once the reaction starts, then at the end we're going to have both the reactants and the products in our reaction flask, and it is not a static situation, but it's a dynamic situation. That is, the reactants are constantly converting to products, and products are constantly converting to the reactants. One way we can kind of visualize this thermodynamic control is if we have two jugs of water that are connected to each other via a tube, right? And the tube is below the surface of water in those two jugs. If I hold those two jugs at the same level, the water level in the two jugs is going to be the same. If I move one of them up, water moves from that to the jug that's lower, and it's going to do that until the level of water reaches gets to be the same in both jugs. So there now I have a situation where the energy of the two is accessible, and the energy difference is not that great for all of the water in the higher jug to come into the lower jug. That's an equilibrium situation. That is how you can think of a reaction getting to equilibrium when the energies are kind of comparable to each other. But if I now move one of the jugs all the way up, then you would see that that jug completely empties out into the lower jug, and you're not going to have any reverse of it. You're not going to see any water going from the lower jug back up to the upper jug. That is when I talk about that reaction goes to completion. And in this example of water in jugs, the reactions in both directions are going to be spontaneous, because just by lowering and raising the jugs, I can have water go back and forth. So that means that that C, the highest level, is energetically accessible. Any questions on this? Hi, John. Welcome.
Hi, Sam. Sorry I'm late.
Oh, no, it's okay. I
Very
totally
late.
missed
I
your
know.
room.
Probably the end here.
No. We're on the
Do you
second
need a
slide.
pen or something?
Oh, wow. Oh, I'm sorry. Did you just start?
Yeah. We're just
Okay,
on
good.
the second slide. So what does thermodynamic control tell us when we talk about thermodynamic control? That I said, we said that C is accessible to us is shown on slide 4. Is that when a reaction is under thermodynamic control, I don't care what the delta G double dagger is. I don't care where the transition state is, because the transition state is accessible. So I'm going to completely disregard that, and I'm only going to look at the products, the reactants, the delta G of the reaction, and determine whether that delta G is positive, negative, how big is it, how small is it, all of that. That when we talk about thermodynamic control of a reaction, or this reaction is governed by thermodynamics, this is what we mean. That is, we're only talking about the delta G of the reaction.
So
Go ahead.
in that case, sorry, Sam, I think I already have. So in that case, thermodynamic control means basically that you're at thermodynamic equilibrium. Is that what you're saying?
No. Hold on one second.
Because I guess I was thinking.
You
Yeah, go ahead.
you're not necessarily at equilibrium, because if the delta G is too large and there is no reverse reaction to speak of, then you're not at equilibrium. Your reaction goes to completion. But
Right.
thermodynamic control tells you the product that you get from this reaction is a product that is thermodynamically more stable than the reactants.
Right. I think maybe what I was going to say was kind of what you were alluding to there. I was just thinking that that thermodynamic control might mean, for instance, that if delta G is small, then there's a simple kind of the temperature determines the percentage that you'll find in both states or something.
So that is an example of a reaction that's under thermodynamic control, but it is
And
not
to
the,
me, that
but
sounds
that
like
is not the
thermodynamic equilibrium.
definition. Yeah. So thermodynamic equilibrium is one of the situation that's under thermodynamic control. Not all equilibria are under thermodynamic control, but not all thermodynamically controlled reactions reach equilibrium. Did that make sense?
Yeah, not yet, but I'm kind of thinking maybe it will later, so I'm going to hang
So
on.
let me then talk about kinetic control, which is the other way that we can control reactions, and then see if that helps. So let's go to slide 5, and here we see a reaction that's under kinetic control. That is here, delta G double dagger is what's important. If C is not energetically accessible, then the reaction doesn't take place. It doesn't matter what delta G is. If delta G double dagger is too high, delta G becomes irrelevant, because we can't really access that. So if the delta G double dagger is greater than the energy that's available, we don't get any energy, because molecules can't make it over the hump of C to make it to B. They basically stay energetically in that valley between A and C.
Do GA?
No. Well,
when you say GB is approximately equal to GA is equilibrium, it makes it sound to me like you're saying that when it gets to equilibrium, the levels change or something. But I can imagine it being at equilibrium with just fewer things in A than in B.
that's exactly it. Yes, with fewer things in A than B.
Yeah.
Yeah. So equilibrium doesn't mean that you have the same amount of stuff on both sides. Equilibrium means that the rate of forward reaction equals the rate of the reverse reaction. That is equilibrium. And that rate equality can take place when you have 5 moles of B and 1 mole of A, right? So that will depend on the G of the reactants and products, and the delta G as to how many moles of what and how many moles of the other, when you calculate the equilibrium constant for the reaction, which is something that we're going to do next week. Next week we're going to get into math and maybe solve a couple of differential equations if we feel like it, to get to all these kinetics and rates equations, and kind of give what I'm talking about here a little bit of a mathematical backbone. So pictorially on this graph, if the delta G forward, delta G double dagger forward, is energetically accessible, that is, A can reach the transition state reactants can react and reach the transition state, but the reverse of it is inaccessible. That is, B, the products can't get together and have enough energy to make it over C, then that's an irreversible reaction. Okay, so irreversible reaction is different than a non-spontaneous reaction or a reaction that goes to completion. An irreversible reaction is kinetic, whereas reaction going to completion is thermodynamic. A reaction goes to completion when delta G is really, really negative and you get negligible reactant concentrations. That's when we get when reaction goes to completion. But irreversible reaction is that the forward reaction is energetically acceptable, but the reverse is not. An irreversible reaction will never reach equilibrium. But if the transition state is energetically accessible to both forward and reverse reactions, then we have a reversible reaction. And in that case, once we have a reversible reaction, then that reaction is no longer under kinetic control. It goes under thermodynamic control because the delta G double dagger from both directions is energetically accessible. Kinetics no longer play a role here. So to show that with the smiley face on 6, for kinetic control, I only care about whether delta G double dagger is accessible or not. I don't care what the G of the products are going to be, right? If I can reach the transition state, the reaction will go forward, regardless of where the free energy of the products are. Where the free energy of the products are, then we'll determine whether it's going to be reversible, whether I'm going to reach equilibrium or not. But if I'm only looking at the forward reaction, then the delta G double dagger is going to be important.
Yeah, I was about to ask, but I think you answered it there. So if we just care about the forward reaction, we look at it that way. But for the reverse reaction, whether it goes to completion, GDE matters.
So, yeah, well, the reverse reaction, when we're under kinetic control, when we're doing a kinetic analysis, we separate out forward reaction and reverse reaction. We look at each separately, and then we put it back together again. But under thermodynamics, we kind of look at both sides because under kinetic control, we're only look at either reactants in transition state or products in the transition state.
Yeah.
So really, kinetic control is thermodynamic control for reaching the transition state. That's how you would distinguish. So we've talked about delta G equals delta H minus T delta S, meaning that free energy is enthalpy minus the product of temperature and entropy. So how does entropy play a role? So how do enthalpy and entropy play a role in the delta G double dagger? Enthalpy we know, right? It's bond breakings, bond making, the bond energies, and all that. That is conceptually pretty simple to understand. What is not easy to understand is the entropy of the transition state. So in the next 2 slides, I'm going to talk a little bit about the entropy of the transition state and the reaction. So slide 7, we're having reaction that a chloroethane looking thing, we have R1, R2, R3, R4. So it means that It's a much longer molecule, but we're not worried about that. This, in a base catalyzed reaction, forms the double bond that you see on the right. How does it do that? On the left, OH minus, that's our base, right? The hydroxide ion, that's our base, comes and plucks the proton that we see is connected to the O with the dashed lines, plucks that, leaves the electrons in the bond between H and carbon there. So that solid line stays there. That solid line kind of falls over to the solid line that's connected to the carbon with chloride. Once it falls over there, chloride leaves. Okay, so the flow of electrons is that the electron pair on O grabs the proton on the H, that proton, then the electron pair flows into the bond between the two carbons. That excess electrons causes chloride with its electrons to leave. So you end up with that double bond. So what can we tell about the delta S double dagger of this reaction? In delta S double dagger, in the transition state, we have hydroxide connected to the hydrogen through a dashed line, and the hydrogen connected to carbon in a dashed line. What happened when we reached this? Where was that hydroxide before it came here? That hydroxide was floating merrily in the solution. It was bonding to this water, bonding to that water, bonding to this, bonding to that. Basically just, floating about, not connected to anything. And that hydroxide has all of its degrees of freedom, whether rotational, translational, however you want to look at it, it has all degrees of freedom. Well, how about the organic moiety? That's the same way too, right? It has clearly it can spin around the carbon-carbon bond. It vibrates at its whatever, the whole molecule is rotating, tumbling, going about. In the transition state, the OH minus has to come in at a specific angle and a specific direction to get the proper overlap with the hydrogen, right? Because as we recall from many, many lectures ago, we're looking at the bond between hydrogen and carbon. We know that there's an anti-bonding orbital behind it, right? So the OH minus has to go into that anti-bonding orbital, has to have an overlap with that anti-bonding orbital. So what happened to that OH minus? That lost almost all of its degrees of freedom. Because now OH minus is somehow connected to this organic molecule, the mass of this organic molecule has gone up. Its rotation has slowed down sufficiently. Its symmetry has been destroyed. By the destruction of that symmetry, we have lost degeneracy of vibrations, that vibrations that used to be equivalent to each other are no longer equivalent to each other, so they become distinct vibrations. All of that. So this transition state is extremely entropically unfavorable because we have created an ordered transition state out of something that was completely disordered. So this reaction at room temperature doesn't take place. right? How can I make it go? I can heat it. If I heat it, what happens is that the T delta S term, or in this case, T delta S double dagger term, becomes more negative. As the temperature goes up, because it's a negative T double S dagger, that becomes more negative. So delta G becomes more negative, and so at higher temperatures, I can then overcome the the entropic unfavorableness of this. Questions on this one example?
Well, so I'm wondering a little bit about what the transition state is here. I could imagine, for instance, the transition state to be something like when the water is gone, but the chlorine hasn't yet left or something. I don't know
Okay.
exactly how that would work.
So this is a complicated transition state. You're going to end up with O dash line to H dash line to carbon, carbon solid line and dash line to the other carbon, carbon dash line to Cl.
Okay, yeah, so that's kind of what I was thinking.
Yeah,
Right.
because the electrons in this case, it's not a stepwise reaction. This one, I mean, you can think of a stepwise reaction where the OH picks off the H, you end up with a carbocation. We're going to see that later on in an example that happens. That a stepwise reaction, you actually end up with a positively charged organic molecule as your intermediate, but then it depends on the electronics of R1, R2, R3, R4, that whether this was going to go stepwise or it's going to go in one step.
Well, and so that's the other thing. R1, R2, R3, R4 are just what are kind of arbitrary ligands? Is that the right thing?
In this case, they're arbitrary. In real life, they're not arbitrary because they affect the electronics
Well, and
of
so
the
that's the
reaction
point
center.
is that just the very idea that it's the chlorine that leaves depends on it being, something that the others aren't, or somehow, I don't know. I mean, it could be, is chlorine just the obvious one no matter what
Yes.
R1, R2, and R3, R4 are?
Well, in this case, we're assuming R1, R2, R3, R4 are carbon-carbon bonded to the center part that we're looking at.
And chlorine isn't?
And chlorine is chlorine carbon bond, but the carbon that's bound to chlorine is connected to a carbon in R2 and it's connected to a carbon in R1. So those
Oh,
are
I
all
see. R1
carbon
and
carbon
R2
bonds.
are other carbon.
Carbon, yeah.
Ah, okay, I get it.
In the way this is written, right? But then I'm going to completely lose everybody by saying this. You can think of like R1 and R2 as being electron donating. If they're electron donating, then they make it a lot easier for chloride to leave. But if there are electron withdrawing groups, then it's going to make it difficult for chloride to leave. So that is all of that is going to change the electronics of the reaction. So as a chemist, you can then design the molecule to force it to go this way or the other by changing the electronics. Hello, Joe.
I love a good chemistry lesson. These
Good.
multiple states with first order reactions, and I'd be curious if any of these have a catalyst type as well, where there's almost one more intermediate reaction.
Yeah, so that is about 3 lectures too early, that conversation. I will be talking about catalysis in the future, but yes, this reaction, as I have written it, this is base catalyzed. and so the OH minus there gets regenerated in a subsequent reaction. So this is base catalyzed. That's correct.
Love it.
Yeah. Okay.
So
So
is
go ahead.
this sorry, very quickly, is this an SN1 or an SN2 type?
This is neither, because
Neither.
this is not a substitution reaction. SN1, SN2 are substitution reactions. This is an elimination reaction. So you can have E1 or E2, meaning first order elimination reaction, second order elimination reaction. This case, this is a second order elimination reaction, because in the transition state, you have two, in the rate determining step, which is the deprotonation, two molecules come together to do that. So this is a second order step. But the thing is that usually when you run this reaction, the concentration of hydroxide is so much, because you're running this, I don't know, in an aqueous solution, the hydroxide, for all intents and purposes, the concentration of it doesn't change during the reaction because there's so much of it. Then we would say this is run under a pseudo first order reaction. And so a lot of second order reactions, because the math of doing a second order reaction becomes complicated, we run those under pseudo first order reactions with respect to each reactant to figure out what the order with respect to that reactant is, or how it does it.
I'm only asking because, sorry.
Would it make it more accurate when you're doing your regressions to find the reaction rates to include the intermediate reactions?
Yes, you must. Absolutely, you must. Because that's the only way you can determine what's a pre-equilibrium, what's a rate determining step. How do you order the reaction steps, and where do you need to focus to determine the rate of the reaction? Yes, for all of these, you have to take the intermediates into account.
Thank you.
So let's look at another example. This one's one of my favorite ones. I'm going to talk about the lower reaction first, and then the upper reaction. The lower reaction is a reaction we have seen before when we were talking about the reactions of acyl groups. This is a carboxylic acid on the left is reacting with an alcohol, and then the product is an ester. This is a condensation reaction, as we talked about. The other product of this reaction is water, and it's condensation because it eliminates water. If I form an ester within a molecule, that is here, in the lower reaction, the carboxylic acid and the hydroxide are in two different molecules. Well, what if the hydroxide and the carboxylic acid are two ends of the same molecule, and I form an internal ester? That's called a lactone. An internal ester is a lactone. So what about that? What can we say about the delta S double dagger of this reaction? So to study the delta G double dagger of this, we first are going to say that as far as the bonds that are being made and are being broken, they're basically the same, right? Same bonds are being made and broken in both of those reactions. So bond energies are going to be the same. But the bottom one is a straight chain molecule, and the top one is a ring. And in a ring, we're going to introduce angle strains, right? Because it's in a ring, and it doesn't have the freedom to move about. Well, as it turns out, if the ring that you're forming has 5 members or 6 members, then the strain in the molecule isn't that important. It is negligible. 6-membered rings and 5-membered rings, yeah, they have some angle strain. We can't deny it. But that angle strain is not enough to affect the delta H of the reaction in a significant manner. That is, it is not enough for most reactions that we talk about to say whether the reaction is going to go or not because of that strain. There are, to be sure, there are reactions where 5 and 6-membered rings, the strain does dictate whether the reaction goes forward or not. But in this case, in lactone formation that I'm talking about, that is not the case. So
Sorry,
basically,
Sam.
go ahead.
Sorry to interrupt, but we see that there's a carbon that has disappeared. Is this on purpose, or is this? So on the left there is 1, 2, 3, 4, 5,
You know,
and on the right
you
there's
know,
4.
too bad Jerry March is dead. Since I don't know if in the 5th edition of this book he fixed it or not. Yes, you're absolutely correct. There has to be an additional CH2 in the ring on the right. So that's that
So
ends up being.
there's nothing missing. It's just that the thing is closed. Is it releasing water? Is it releasing anything? No, nothing. It's just that the molecule is closing.
Yes.
And it actually is a 6-membered ring then at the end.
Yes, it's a 6-membered ring. Yeah, we have a missing CH2 in that picture. Oh my God, March made a mistake. So March is God, or was. This advanced organic
He
chemistry.
probably died of embarrassment.
I know. He was born in like the 20s or something like that. But anybody who has gone through advanced chemistries, either as an undergrad or in graduate school, owns this book, Advanced Organic Chemistry by Jerry March. It is one of those kind of Bibles of chemistry. In the inorganic side, if you're interested, it's Cotton and Wilkinson. Those two wrote the treatise. Anyway, so yes, as Shamash said, that's a 6-membered ring. And so we look at the bottom one and the top one. We see that the top one goes a lot faster than the bottom one. And the answer is why? I mean, the question is why? The answer is that the delta S in the top one is a lot more favorable because we start with one molecule and then we end up with one molecule. And everything is right there next to each other. There isn't a lot of movement of atoms for that reaction to take place. That is, as the molecule is going through its normal tumbling and rotating and going around bonds and all that, it comes into the proper orientation for this reaction to take place. But in the bottom one, we have to bring 2 molecules together in the transition state. I'm talking about the transition state now, right? Not the actual reaction itself. We have to bring 2 molecules together. We're going to destroy a lot of degrees of freedom when we bring them together to form the transition state. So that transition state is entropically a lot more unfavorable than the top one. And so the delta G double dagger for the bottom one is higher, so the rate of the reaction is slower. Why is it slower? Because fewer molecules reach the energy required to clear the delta G double dagger, right? All the molecules are all distributed based on Boltzmann distribution as far as energy is concerned. So some of them at the high end will have enough energy to go over, but because the T delta S is not as significant at lower temperatures, you have less molecules at the right end of the Boltzmann distribution. So it goes a lot slower. Questions?
Does it require an activation energy as well, or
Yeah,
it's
yeah.
the same
Well,
energy?
the delta G double dagger is the activation energy. So delta double dagger is a component of the activation energy.
Whereas the one on the top is completely spontaneous. Whenever you place the molecule, it will immediately.
They both are, right? One goes faster than the other. At the if you look at the reactions at constant temperature, both of them are run at the same temperature. You'll see that the top one goes a lot faster than the bottom one, because the top one is a lot more entropically favorable than the bottom. The transition state for the top.
Without having the transition states, I asked a rhetorical question, would doing a linear regression in this series result in non-linear mathematics?
I don't
Higher
think.
orders.
Yeah, I don't think I
of
understood what you
regressions.
said.
So that the regressions would end up with variables that assume that it has multiple orders rather than their linear equations.
Unfortunately, that's a level of mathematics that I don't know much about. So
When
I
you do the
can't.
catalyst math, it'll do the same exact thing.
Okay. Yeah, yes. I don't do math. So I'm a descriptive chemist. So hopefully when we get there, you're going to be in the room to tell us what's going on mathematically.
Often what happens is that the reverse reactions with a catalyst end up being described as insignificant. And so then it's like people skip a step in the linear regressions, thinking that there is no step intermediate. And so it ends up being a higher order equation because a reaction rate in between two steps is so ridiculously fast that it was never even considered.
Okay. So let's go to slide 9. That is where kind of I wanted to get to today. So the reactants here are A. And when we run the reaction, we'll see that immediately we're going to form C. But then after a while, the reaction changes, and most of what we find in the flask is going to be B. A are the reactants in this diagram. A are the reactants. C is the kinetic product. B is the thermodynamic product. So what happens is that when A undergoes reaction, A to C has a much smaller activation barrier. Delta G double dagger C is much smaller than delta G double dagger B. So very quickly, A gets converted to C. However, if delta C double dagger in the reverse and delta G double dagger B are both of them energetically accessible, then we'll see over time C converts back to A, then A converts to B, right? It goes back and forth between A, B, and C. But since B is a much lower energy state, the majority of the products end up in B. So C is the kinetic product, B is the thermodynamic product. This happens a lot. And in the next slide, I have a rather complicated reaction, complicated for us. And that's the reverse of the reaction we talked about, the elimination reaction that we talked about. In the elimination reaction on slide 7, we formed a double bond by getting rid of a proton and a halide. Here we're adding a proton and a halide across a double bond. So this is exactly the opposite of that reaction. So what happens? What does happen here? What happens is that initially we add a proton across the double bond on the right, and we end up with that secondary carbocation, a cation, a carbon bearing a positive charge, where that carbon is connected to 2 other carbons. Very fast, the bromide of that HBr will attach itself to that plus. And so the kinetic product that you get is going to be that 3-bromo 2-ene product on the right-hand side. But that is because the secondary carbocation that I got is more energetically favorable, right? That is reaction of that. The secondary one as an intermediate is energetically favorable, and the reaction of that with bromide has almost no activation barrier, right? It's like very, very, very small activation barrier. But I know that if I were to put the bromine at the end, the compound that's at the bottom, that is a much more thermodynamically stable molecule. Why? Because now the double bond is in the middle. Double bonds in the middle are more stable than double bonds at the end, because you have the methyl groups electronically stabilize that double bond. And the bromine being at the end is more energetically favorable because bromine is large. It's almost as large as a methyl group. And so when it's in the middle, it keeps bumping into other atoms, and so makes the rotation along the carbon-carbon bond more complicated. It makes it more energetically unfavorable because it's bulky and bumps into things. But when it's at the end, it's kind of free. So those rotations are a lot freer, and so that's a much more stable. Also, bromine being where it is with respect to the double bond, having another methyl on the other side is going to electronically stabilize that double bond more than when it's not there. And so if I let this sit, what I'll see is that the carbocation gets reformed, but then it moves to put the carbocation at the end, and the bromine reacts with that. When I run the reaction quickly, I end up with 98% of the 2-bromo and 2% of the 1-bromo. So the kinetic product is 98%, but the thermodynamic product is 2%. Now, I can change that, right? I can now change the temperature of the reaction. If I run this at a much higher temperature, then I'm gonna get a lot more of the thermodynamic product because I make the travel between all those peaks a lot easier, and so everybody will end up over at the thermodynamic product. But if I were to run this reaction and after like 2 minutes put it into dry acetone or liquid nitrogen to quench it, to freeze it so that reaction doesn't take place anymore, then almost 100% of the products that I'm going to get are going to be the kinetic products, none of the thermodynamic products. So I can play with reaction conditions. I can play with solvents. You know, I can put in solvents here that would stabilize a primary carbocation much better than they would a secondary carbocation. I can so I can play with reaction conditions to force this going into kinetic or thermodynamic way. In the last slide, slide 11, I have the energy diagram for this. That in the middle is that carbocation that we talked about. It can go to the left, the kinetic product, because it has a much lower activation energy, and give me the 2-bromo, and eventually it can move to C, which is on the right-hand side, the thermodynamic. So that concludes what I was going to say today. As I said, next week I'll kind of talk a little bit more about this and then get to the derivation of rate equations and equilibrium constants and things like that. It's now open for questions.
I got another rhetorical one. So, given that you can change the thermodynamics, I would assume then that the reaction rates can change. However, the ice tables do not.
Sorry, what doesn't change?
Your initial change in endpoint tables, or at least the mechanism.
I'm not really sure if I understand.
The fact that you still have a chemical pathway between still requires the chemical pathway, even though the same chemical pathways at different thermodynamics could result in different linear regressions, causing you different reaction rates.
So each pathway is unique and gives rise to the same products. What would change is not how the pathway behaves, but which pathway you're going to take. That is by changing the thermodynamic conditions of the reaction. By changing reaction conditions, I can make some pathways be available and some pathways not be available. I can't change the pathway itself, right?
But you could have, with different things that you change, you could end up with linear regressions that result in different reaction rates.
Yes,
And
yes,
you've never
absolutely.
been
Reaction.
able to change the pathway.
Yeah.
happens.
Reaction rates are completely under my control. I can I can play with reaction conditions to change relative reaction rates, change rates, make one be completely zero. You know, I can change reaction rates, but I can't change the pathway. That is, I can make it go down the same pathway faster, slower, or I can make it go down another pathway. But going down it, I can't change a pathway. I can either shift pathways or shift the speed in the pathway. So for example, I can only drive down the roads, and I can determine the speed of my car. I can't create a new road. I can decide I want to go down this road or the other road, but I can't change the road and say no. This I-80, I want it to go north south now. I can't do that.
And then I'm going to add another little fun little detail. So a road could be windy, but should you add a catalyst, it might appear like it's straight, even though it can take a new pathway with a catalyst that looks straight, even though the windy road still exists.
I would change your analogy slightly. I would say I have a road that winds up a mountain and comes down, but then I can put a tunnel there, right? And so now the energy for going from city A to city B, right? It's the same. My potential energy at city A is the same as it was before. Potential energy at city B is what it was before, but the activation energy for going from city A to city B has not changed because of this tunnel, because by introducing this tunnel, I have created a new path that doesn't require the same activation energy. So that really is catalysis, is that you create a new path that has a lower activation energy. And so sometimes you can have a molar catalyst, and sometimes you can have an actual catalyst. But in any event, they both lower they give you another pathway that has a lower activation energy than the one you were looking at before. It's
And I
not
would
this.
also apply on top of how you changed it that the scenic pathway can still exist even though we can foul the catalyst and
Absolutely.
block the tunnel.
Yeah. That goes also, but the thing is that most people will take the tunnel. There's some crazy guys who have like way too much energy, and they're like jumping up and down, and it's like, let's go to the top of the hill, right? Those guys still go to the top of the hill, but most people will take the tunnel.
Cool, thank you.
Sure, thank you for the questions.
So when I look at your at that last diagram, I'm sorry, Sam, I got distracted for a little while, so you may have talked about this. It looks like you can read that for lots of possible situations. One would be starting with the reactant being the intermediate state, and it looks like it's kind of set up to look at it that way. If the reactant is the intermediate state, then you're talking about stuff going over the hill to B and stuff going over the hill to C, and I think it all's kind of self-explanatory. And I see how at low temperature, the path to C, even though it's energetically advantageous at C, is blocked off because of the energy of the intermediate state. Um, but I think it is the case when you say major product at high temperature for C. I think you could read that basically no matter where you start, you're going to end up with more things at C. You could start at C, you could start at the intermediate state, you could start at B or A, B, or C. You're going to end up with most stuff at C if you're at high temperature.
Absolutely, yes.
Yeah.
Yeah, that's
Okay.
correct, because once you're at high temperature, all of these energy states, right? B transition state A to B, A transition state A to C, and C, all those 5 energy points will be accessible to you. So you're going back and forth, but then you end up at the well, which is C.
Yeah.
Yeah.
So
That's fun.
if given enough time, even if the temperature is constant, would these B products become C with time simply because it's more thermodynamically favorable, or will they be stable at B?
Depends on where they are. If at the environment that they're at, the transition state A to C is going to be accessible, then yes. If you let it sit there, eventually all the products will be C.
That's right. Well, so that's interesting too, of course, because the point is that no matter what the temperature is, if you wait long enough, but that waiting long enough can be enormous because of the kind of exponential behavior of the rate on the height of that energy barrier. Is that
Right.
fair to say?
Yes.
Yeah.
And the reagents that are active for it. So one of my favorite ones to bring people's attention to is the iodine clock, until it finally reacts and uses up all the reagents.
Yeah.
So it ends up fighting for intermediate reagents, and so they're not available. So the reaction goes back and forth in colors.
That is my wife and I used to run this a science program at my kids' elementary school when they were there, and the iodine clock experiment was always a staple, and it is such a fun thing to do with kids. Yeah. So this activation barrier
So,
and irreversible reactions. I mean, we face this on a daily basis. Burning wood is one such thing. So burning wood is a spontaneous reaction, meaning that the delta G is extremely negative, and it's an irreversible reaction, meaning that you can't get carbon dioxide and water and form protein out of them, right? It, it, you can, but it's going to be extremely energetically unfavorable to do that. So it's a spontaneous reaction, it's an irreversible reaction, but it has such a high activation energy that wood sits there for millennia and doesn't react with oxygen. But as soon as you tickle it with some flame, it just goes, right? It goes spontaneously, irreversibly, and it goes to completion. That's Hi, Hanson.
Hey, how's it going, SKT? So I think I just came in, but I heard Shamash's question. I think if I heard it correctly, Shamash was asking if two energy level, one is higher than the other, would at time infinity would, let's say A is higher, energy level is higher than B, would at time infinity would all the product be B? Is that the question?
Uh, I don't know if that was the question, but the answer is no, right? Because
Right.
you
Yeah.
reach equilibrium.
Right.
So you're going to have
Yeah.
some A and some B.
Right. And then
But
depending on temperature, right?
right,
When
right.
you have a lower temperature, there will be more B than A, and higher temperature there will be uh, closer
Yes,
to
to equilibrium.
half and half.
Yeah.
So yeah, I wasn't sure what the
Well,
yeah
no, the
what's the
question was
original question.
the question was that if like this system that's on slide 11, if we let this sit at, you know, at a temperature where all the activation energies are accessible, then what happens, and we say most of the stuff is going to then be C.
Yeah,
Because
yeah.
yeah,
I mean, most of the stuff,
but you
but
still,
not
most
all.
of them, not all,
Yeah,
yes, exactly, because if they are energetically accessible, that means you're in an equilibrium position, but at that temperature most of the products are going to be C.
right. Yeah, and the lower the temperature, the more the stuff would be.
The lower the temperature depends on where you are,
Right. Yeah. I
right?
mean, it's like a two-edged swords.
Because you can run the
You have to
reaction and then
go
quench it, right?
right. You have
Dump
to
it into
go
ice
over the
water,
hurdle. Yeah.
and then you are where you are,
Right.
and
Yeah.
you've
I mean,
frozen it.
you have to go over the hurdle.
Yes.
Yeah.
So I think once we're at an energy where delta G double dagger for both reactions is accessible, then increasing or decreasing temperature changes the rate of reactions. Oh, no, it changes equilibrium too. Right. Okay, I take it back. Sorry, I take it back. Yeah.
Yeah. Then, I mean, if we do take into account some like quantum tunneling, then there's a little bit of a difference.
Oh yeah. let's 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 not go there.
Let's get Benjamin in here before we start that conversation.
I think I was actually thinking about this. Once I'm done with all this, I think it would be interesting for me to give a talk about my thesis, if I can still remember, from 30 years ago, because this is really what I did. Measuring delta G double daggers and delta S double daggers and reaction rates and tunneling and kinetic isotope effects and all that for my system. So I think that might be an interesting one.
There's also a really good conversation to be had with the four different types of reaction vessels, whether or not it's a plug flow reactor, a continuous stirred batch reactor, a batch reactor, or a fluidized bed reactor.
Are you doing welding, Joe?
I'm at a rubber press manufacturing plant programming their presses. But continuous stirred batch reactor, plug flow reactor, fluidized bed reactor, or batch reactor all have different ways that they change the concentrations within the reactor.
It sounds like Joe is
But
coming to us from like the mechanical room in hell.
but there you're basically using the Arrhenius equation, right, to measure these things.
Not familiar with that equation, honestly.
Sorry, I didn't hear what you said.
Sorry, I wasn't familiar with that equation.
Oh, okay. Come by next week.
What equation? I didn't hear.
Arrhenius. That
Arrhenius?
Yeah, because that it based on that you can calculate like the temperature and the time and based on the concentrations and stuff.
I mean, I thought I would think with that just a corollary of the free energy and um, the the dynamic equation concentration and just the thermodynamic reaction equation.
Dynamically, it changes the concentrations and equilibriums because the point at which you inject A concentration is different than if you start with everything in an initial batch versus you inject it continuously into a pipeline, or you inject it into a tank that is already stirring and in an equilibrium.
So, I mean, depend on the contact area and all that. Right? Yeah, so I suppose you guys are talking about the how the reactants are arranged in spatially.
Yeah, I was just adding one more dynamic that I know is heavily studied.
Yeah, I mean, I think the all the thermodynamic equation, the reaction equation is assuming that they're in sufficient contact. But if you have a geometry, the initial condition, that geometry or boundary condition, a different contact, then of course it's gonna change. I mean, the uh, local, the yeah, reactants and how they get into contact.
That's not really a huge consideration in solution phase chemistry because the thing's being stirred vigorously, so you're always presenting new orientations at sufficiently high concentrations such that the statistical mechanical effects wash out. But in gas phase, that becomes significant, if I understood you correctly.
Oh, I was trying to understand the what Joe was saying. I mean, I think if it is gaseous, then it's faster, especially high temperature, high pressure. Uh, the admixture would be faster, so it gets into contact pretty soon. Then the you have kind of these reaction. Uh, well, actually, I mean
So
the
formation of a mixture is faster, or is
yeah, I mean
that
like let's say you have. I mean, just to take the extreme examples, right? I mean, if you put two uh, uh, let's say viscous fluid um, that's or even solid, right? You just try to react, and then as opposed to gaseous mixture that try to react, that those are two different. No, you have two different velocity. I mean, the speed, right? And then if you have solid and
Concentrations.
only the not even concentration, right? Because if you have a solid, uh, how do you define the concentration at the reaction? Because they're not even mixed. You only have a boundary that are interface that are coming into
so
contact, and then
that's
as opposed to
no, that is just one consideration, right? So that is only the you're just taking into account the number of collisions and the geometry of collisions.
right, exactly. So
But
like
the thing is that in solutions you get a whole lot of solvent effects, right? You
yeah,
get
that's exactly
stabilization
what
of
I was saying,
transition
right?
state or intermediate.
Yeah, yeah.
So
So
you
that's
can't you
exactly what I was saying.
yeah. Okay.
It's changing. I mean, comparing to solids to gas. I mean, the two extremes, right? Two
Yes.
solid to gas, and then you can have intermediate conditions, say viscous fluids, right? Extremely viscous fluid like honey and all that. Um, the two less viscous to dry water or dry fluids
Yeah.
to gas and to very the energetic gas. I mean these are all very different.
This is where I love Antoine's equation, at least when it comes to partial vapor pressures. So that way you can come up with concentrations in order to do rate of reactions. I couldn't drop it without bringing it up.
That's why we have like jets or the injection and combustion, like flames. How you that mix the fuels in the engine.
Okay. If there are no more questions, Shamash, what are you doing on Wednesday?
On Wednesday, we will do Bayesian epistemology. So hot topic, everybody's favorite, Bayes. So we will do that. Sorry, I'm getting a call. Sorry, I got a call. 1 second. And Wissam is asking, when does philosophy of chemistry series start? I'm really not an expert on that one. I know very little about the
That's hilarious.
Philosophy of chemistry.
I saw that. What is
Is
philosophy of
chemistry real?
chemistry?
I don't know. He said it's hot shit right now.
Must
Tell
be
you what.
I've been telling everyone that I would go back to school and I would get a psychology degree and then use chemistry mathematics in order to map the transfer of ideas.
So maybe
Psychology is not a real subject. It can't be studied.
maybe we should ask Wissam to come and give the philosophy
Yeah,
of chemistry.
I think Wissam is the guy actually, like because most people will be
he's the
interested
only guy
in what.
who knows what philosophy
No,
of
I
chemistry
think
is.
he's trolling. He's trolling.
Tell you what, in any event, we are starting this discourse for the Discord server for the scientific discourse. If you scroll like 5 messages up, you will find a permanent link to join. So any paper, any article you read, the Discord server is very primitive for now. But when I get a moment, I will create a better one. And whatever it is that you want to discuss with people, can just paste the link there, and then we can let's say, oh, this person knows about whatever. So you can ask people about your work, review other people's work. So we're trying to start a small community here. If you're interested and you are on Discord, please join.
Thank you very much. John, besides talking about metachemistry, what are you going to talk about on Friday?
So on Friday, we're going to finish up what I'm calling the Stellar Aberration series. I've become really convinced that I gave this series the worst possible name because I think in some sense it's the best thing I've done. But, but it really sounds boring from that standpoint. What we're going to do is we're going to start where we left off last time after the massive success of the wave theory of Fresnel's ether drag hypothesis. Everybody was feeling really good about this. And then, eventually all hell broke loose with the Michelson-Morley experiment, and then leading to relativity. There's a few things we're going to talk about on the way to that, but talk about how the ether finally outlived its usefulness, even though by 1870 everybody knew that it had to exist. 20 years later, it was becoming pretty clear that it didn't. And that's what we're going to get to, and then we're going to introduce the theory of relativity, and then I'm going to stop. I'm going to stop right where everybody wants me to start, because we've talked about relativity in the past, and we'll talk about it in the future.
Very good. Or if you go really fast, you can hear the previous ones live.
That's right.
All right. Well, thank you everyone for coming to our room, and don't forget to go to Shamash and John's rooms, and Ben has some rooms here and there. Hope to see you all there. I'm going to leave you because of the recent death in my family. I'm going to leave you with "Death Don't Have No Mercy in This Land." It's an old song by Reverend Gary Davis, but I'm playing you the Amethyst Kia version, relatively new. I hope you enjoy it. The room will end after the song is done. Take care, everyone.
Death don't have no mercy in its land. Death don't have no mercy in its land. Come to your house, it won't stay long. Look in the bed, somebody's gone. Death don't have no mercy in its land. Death will go all in your family in its land. Death will go